is day 2, lesson 2, Earth's atmosphere, in unit 1. So our objectives in this lesson, that you can describe the composition of the Earth's atmosphere. There's going to be some percentages that we want you to know of the different elements that are in the air. You can identify the sources of the greenhouse effect. So there's more than one, but basically you can describe the greenhouse effect. Define air pressure, so there's going to be a definition you need to know, and identify its metric measurements. I'll show you several measurements, but I want you to be at least identify. You don't have to list them, but if they're given a list, then you can at least circle them or check them off or something like that. Interpret the relationship between air pressure and altitude from a graph. So in science, we often show and demonstrate things in graph forms, so that we can compare and contrast different things here. So you're going to be looking at a graph today and learn how to analyze that graph. Plot and that's supposed to be analyze, not analysis. Typo there. Plot and analyze to discover and explain how the layers of the atmosphere are divided. We just didn't name them to name them. There's a reason why we named them or gave them a name. And finally, list the layers of atmosphere in order and compare their properties. So know a few things about each one of the layers. That's what today's objectives are. All right. So as we go through these notes, you have what are called guided notes in front of you. I'll have everything written up on the screen and give you places or blanks where you need to fill in certain, important details to make sure that you're not just, falling asleep on me. So the composition of the Earth's atmosphere. The Earth's atmosphere is mainly made up of 3 things. Nitrogen, which is the majority of the Earth's atmosphere. 78% nitrogen. Yep, that's the first blank. Oxygen, 21%, definitely far less than half. And then you just have a tiny, tiny bit of water vapor compared to the whole rest of the atmosphere. Oh, sorry, 4 things. Carbon dioxide. But there are some other gases, but they're so insignificant, or there's other gases and molecules that are in the air, but they're so tiny in comparison to those. Like they would be 0.0000000, very, very tiny. No, it's supposed to be a dash, yeah. So carbon dioxide is 0.037%, so not even a full percent. In comparison to the rest, think of it like, percentage to decimals, 78% would be like 78 cents of a dollar. Oxygen, 21 cents for the dollar. Water vapor, 0 to 4 cents to the dollar. And finally, carbon dioxide would be like saying, I'm sorry, not 4 cents. Yeah, 4 cents. And the carbon dioxide would be like less than a penny. Really, it'd be like less than a penny. So take a look at water vapor. I think that's interesting that it has a range 0 to 4%. If you were to look up into the sky, is there any indication you might have that there may not be much water vapor in the sky that's right above you? Mm-hmm. And that's what we're going to get to on this next thing. Most gases are clear. You can't see them at all. Water vapor, though, you can kind of see sometimes. It was foggy. Okay, so you see fog. Clouds. Clouds is water vapor. It's not a gas. It's water. What you see up in there. Now, it's water that's attached to little specks of dust and things, but that's what a cloud is. A cloud is actually water vapor. So when it says that range 0 to 4%, that's because if wherever you happen to be, you don't see any clouds, then you know the water vapor is going to be quite low in that particular spot. Right. So gases, though, are unevenly distributed in the atmosphere. So yeah, you have 78% nitrogen, blah, 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 but they're not spread evenly as you go up in the air. Okay. Out of the 120 kilometers that we consider our Earth's atmosphere, so if you think about 120 kilometers, 99% of all of our atmospheric gases, including our water vapor, extend only 30 kilometers above the Earth's surface. So only the first 30 kilometers is where all those gases are. 99% of that. So the rest of, the 110 kilometers in the atmosphere, there's just little specks of those elements floating around, or those gases. Most weather occurs in only the first 10 to 15 kilometers of the Earth's atmosphere. So our Earth's atmosphere is 120 kilometers, but only the first 10 to 15. Think of it, okay, Earth's atmosphere, and that means this much of it, clear down here, is where all the weather occurs, and this much of it maybe is where all the gases are located. Let me see if I need to move that for you. Hold on, so you can see. It is in print on your paper. Nitrogen, oxygen, argon, so that's one of those other elements that's very little of. Water vapor, carbon dioxide, and most other gases are all invisible. That's what we were just saying. But clouds are not a gas, but condensed vapor in the forms of liquid water droplets. So that is liquid. Ground-based smog, which looks like a cloud at the ground, is visible and contains reactants of nitrogen and ozone. So we're going to be talking about ozone today, but the ozone that's at the ground that you see as smog is actually, smog is primarily ozone at the ground level. We'll be talking about ozone that's up in the air. So ozone at the ground, would you consider that good or bad? Bad. Smog is bad, right? So ozone at the ground surface is bad. I guess what I'm trying to get at I'm probably letting you know that there is good ozone. Okay. It's just not at the ground. Pressure and density. That's what it says, air pressure at the top. The amount of force exerted over an area of surface. So this is a definition you need to write in. You may be asked on a test to define air pressure. And I'm looking for amount of force exerted. That's one of those $1 million words. Over an area of surface. Okay, so pressure, pushing down on you is the amount of pushing down on over an area. We can measure this in different types of units. Pascals, or what normally you hear is pounds per square inch. Have you ever heard that term, someone say PSI before, or pounds per square inch? I hear it all the time when I go take my car into the mechanics or something like that. And especially when I have to get my tires changed. You ever heard of, the air in the tire is so much PSIs? Or pounds per square inch? You need to have something about it. You never heard of it? Yeah. You will probably hear it. Torr, atmosphere, or ATMs, you'll see it abbreviated. It's an atmosphere. Millimeters of mercury. On the periodic table, back there, if you ever get a chance to go up and look at it sometime, the letters Hg, this is funny because it's one of the elements that on the periodic table that doesn't begin with the letter that it actually starts with. The word mercury starts with the letter M, but its symbol is Hg because M is already pretty much being used by some other element. So Hg. So that's millimeters of mercury. Think about, why would they use mercury? If you think of a column or a tube, what they've done to measure pressure is if they, in a vacuum sealed tube, they push down on it, and on one side, on the other tube, they have mercury. You guys know what mercury looks like? Or things, it's that liquid, it looks like metal. If you like the old thermometers, if you ever broken an old thermometer, played with mercury before, it's kind of poisonous and not supposed to do it. Yeah. Those of us are older, we used to do it in class all the time before they told, you're not allowed to have mercury out. It's poisonous and you shouldn't let your students play with mercury. So in the old thermometers, the mercury would rise up the thermometer the hotter it got, right? Same thing with pressure. When you put pressure on the column, what they would do is they'd measure the length of that mercury rising up the tube. Okay, so that's where, how they say millimeters of mercury. They changed a liquid and are measuring it by length. So we're measuring length there. And bar. You might have heard of bar maybe on the Weather Channel. Ever heard of an isobar? Okay. ISO means same. So in the Weather Channel, they always talk about, oh, the ISO bar is here. They're talking about the same pressure in a certain area. So they measure in weather a lot of times. They'll measure pressure. So I have some conversions. You do not need to know these. You do not even need to write these down, but just an idea. So 1 atmosphere is equal to 0.98 bars, or barometric. You've heard of barometric pressure maybe sometimes? That's where that bar comes from. Barometric, bar, metric. Get the idea? So some of these measurements that you see on here are standard units of measurements, and some of them are metric. Can you maybe identify at least one on this list if you were to go and say, hey, I need to do this, and over in England, and they're like, oh, you're a bloody Yank. Which one of those do you think you could probably pull off right now and say, that's not metric? The first one, yeah. Pounds. That's not a metric measurement. That's a standard measurement. Okay. Torr. And actually I need to look that one up. I think that's also standard as well. I'm not used to that one. Atmosphere, though. An atmosphere is actually, 1 atmosphere is equal to, I had this on my paper. Is it on your paper? I think I added on yours.
760.
Okay, let me write that down. One, does it say atmosphere? Is equal to 760 millimeters of mercury. Is that what I have on there? Okay. So even if you don't know what measurement an atmosphere is, whether it's metric or standard, how about millimeters of mercury? Does millimeters of mercury sound like metric, or does it sound like standard?
Sounds like metric.
Yeah, you hear the meter in there. So on your paper, I asked you to put a star next to, that's what the asterisk is. So let's put a star next to millimeters of mercury. That is metric. And if that's equal to ATMs, that means that, yeah, ATM. Yeah, we're going to get our money's worth. Atmosphere, that's also the metric system. And so is bar, like isobar. So bars is just another unit of measure. You can have a millibar, you can have a centibar, not cinnabon, cinnabar, things like that. So those three are the ones that you might see back and forth measuring pressure. It just depends on how big of an area you're using. For example, if I was measuring the distance from here to Fisher's, and if the only thing I had was a inch to measure it, would I want to measure that far? That number would be huge, right? So it's better to use a different unit of measure, like a mile, to measure great big distances. Same thing between a bar and millimeter mercury and atmosphere. It just depends on how big of an area you're measuring. So that's why they'll change them in, because they still want the number to be small. Okay. Let's see here. Take that off. So we're looking at pressure and density. There's a lot. Hold on, let me fix. Here we go. The only way our atmosphere has held to the Earth is with this pressure that we just talked about, our different units. It's holding all those gases against there with pressure. But what is that pressure? And normally you think of pressure as someone pushing on you, but actually pressure with our atmosphere is a pull. What's pulling all those gases to our Earth to keep it around us? Gravity, yeah. Our gravity pulls those gases towards the Earth's surface. A whole column of gas weighs 4.7 psi's, or pounds per square inch. and remember that's standard unit, at sea level. So that means if you're down in Florida and you're looking at the ocean, that's how much the air is going to weigh above you. That's considered a lot. Now think of what would be the opposite of that. Where could you stand in the United States where you wouldn't have that much pressure on you? A mountain, yeah. The higher you go up in elevation or altitude, altitude and elevation means the same thing. The higher you go up, normally we say elevation when we're talking about ground. We talk about altitude when we go into the sky. But it's still a distance away from something, where elevation is the distance from sea level up, and altitude is from the ground up to space, basically. Let's see. It says a pressure of, that's 1,013.25 millibars, or 29.92, and that is inches of mercury. Okay, so the difference between here, they used inches of mercury because that's what we'd say here in the United States. Again, because it's a standard unit of measure that only the United States uses. Anywhere else, if you're watching a weather report or speaking to a scientist from a different country, or any scientist in the scientific community, they would say millimeters of mercury. Okay, so scientists here in the United States still use the metric system. That's why we're focusing it so much, even here in the United States. But common everyday people in the United States use standard units. Air density is the number of molecules in a given space, though. So not the pressure, but how many molecules that might be in a given area. Let's take a look at this graph and see if we can interpret it. So this is one of our objectives here, to make sure you understand it. I think I put a check for understanding off this side. So my check for understanding is off to the side of your slide. You can look at your slide or your paper, and here's my question for you. Sometimes graphs can be misinterpreted with the information that it's trying to explain. Pictures are always worth 1,000 words. Graphs are definitely too. According to that graph, as you go up in the atmosphere or increase in altitude, the air pressure always does what? You think the air pressure increases as you go up in your altitude? So I'm going to go back that slide and let's see. You think it goes down? So that's exactly why we talk about this, to make sure you do understand what this graph is trying to tell you. So let's look at the values that are on the bottom and the top. At the bottom of the graph, you see the words low and you see the words high, and you see the word increasing. Well, what are we increasing? We're increasing, and there is word that's missing here. How about air pressure or pressure? So air pressure is showing that it's increasing as you go from left to right. On the vertical scale, you see the word altitude. So as you're going up. For example, can you estimate, is the air pressure high or low at 400 kilometers? Look at your graph. Here's 400 kilometers. So look where it intersects this line. If you drop down and look below, is that low or high? Low. So would you say high altitude equals low pressure? I guess I could have chose a different marker. You could actually see. I'll write that again for you. High altitude equals low pressure. Does that make sense? You have less molecules on top of you. The lower you down in elevation, the more molecules you have above your head. Higher pressure. And we can demonstrate this with the graph too. if we say what is the air pressure high or low at, say, 100, at 100 kilometers, so you look across until you hit that line, there it is, and drop it down, and it's not exactly over by the word high, but it is at least higher than the low one that we dropped down, right? So this is how you would read the graph. Let's go back to our question then. So as you go up in the Earth's atmosphere, the air pressure always decreases. Yeah, write that in there for you. It decreases. My pen tool just went away. So here's a profile of vertical pressure. Again, another graph that you can see. You see on the bottom it shows pressure. What's the pressure being measured in this time? Look at the bottom of the graph on your picture.
So what's it being measured in?
Okay. Millibar. Yeah. Millibar. If it's a metric system, we don't say metric, whatever, metric. We don't use the word metric. We just, it's the little m, so that's that milli.
Okay.
So it's a millibar. Yeah, so we're increasing in millibar, so we are using the metric system. And our altitude is being measured in kilometers, yes. So it says atmospheric pressure decreases rapidly with height. So not only will it decrease, but the higher you go, it'll decrease very, very fast. You see Mount Everest there, it's decreasing below of your altitude. Let's see. Oh, if you notice there on one side, your altitude, this graph right here on the right side, they're measuring the altitude in kilometers or kilometers. On the right side, it says MI, so it's measured in miles, so it just shows the comparison of miles. So less than 10 miles, look at the difference in that air pressure. The air pressure is getting closer and closer to zero, and it goes up very, very fast. So there at the top of Mount Everest, it looks like you're at only about 5 miles high, and it's already decreased from about 1,000 down to 300. So 1,000 millibars down to 300 millibars. That's a really sharp decrease.
Actually, I have to leave now.
So the atmosphere, temperature is changed in the atmosphere. Let's make sure where you're at. Okay, so on the top of page 3, you have a blank there. It says the warming of the atmosphere by absorbing and emitting, so pulling in and letting go infrared radiation while allowing shortwave radiation to pass through. Radiation, that's like heat, okay, from the sun, that's radiation. The gases mainly responsible for the Earth's atmosphere greenhouse effect are water vapor and carbon dioxide. You might want to underline or highlight those two words there.
Okay.
So water vapor and carbon dioxide, that's what causes that greenhouse effect. All right? And the greenhouse effect is just like a greenhouse. If you think of a greenhouse, what does it do? It helps keep plants warm on the inside. Well, that greenhouse effect keeps our planet warm. Otherwise, all that heat, just because the sun's shining, think of all the sun that's shining on other planets and things. Are they as hot as the Earth? No, because there's no atmosphere to hold in that heat. We need an atmosphere in order to have heat. There is another planet in our solar system that is extremely hot. It's Venus. Venus is the hottest. Why is Venus, which I don't know if you know this, that Venus is further away from the Earth or from the Sun than than Mercury? Mercury is actually the closest planet.
Okay.
Venus is the next planet out. It has lots and lots of clouds and atmosphere around it, and the greenhouse effect of that particular planet gets it super hot, even hotter than the planet that's closest to the sun.
Wow.
So yeah, distance does help to a planet itself, but that atmosphere plays a significant role in keeping the planet warm. So it's important we know something about our atmosphere because we need it. So the next blank there is lapse rate. Lapse rate is the rate in which air temperature decreases with height. So as you go up in the sky, the temperature gets colder. Yeah. You might know this if you've ever gone up the mountain, you notice that it's colder at the top of the mountain than it's the lower of the mountain.
Right.
So we'll find in some times where we have a lapse rate. The standard lapse rate in the lower atmosphere, and that's important too, that you underline or circle the word lower atmosphere. So the bottom of our atmosphere, closest to the Earth, is about 6.5 Celsius per 1 kilometer. So we're going to drop 6 degrees for every kilometer you go up. Or 3.6 degrees Fahrenheit for every 1,000 feet you go up.
That makes sense.
Okay? Go up, it's going to get colder.
Yeah.
This is, again, I'm emphasizing in the lower atmosphere.
Okay.
So what do you think I'm going to be implying here a little bit?
It's going to change.
It may change, yeah. So we're going to look at something. Yeah. So we have this thing called temperature inversion. And that's just a fancy way of saying that the temperature is going to change. So as you increase, temperature's inversion is just basically an increase in air temperature with height, often simply just called an inversion. It means the temperature is going to change. Suddenly start rising instead of falling. So we're going to be investigating some layers. I'm going to pause this. And on your paper, you have some background. I want you to read the background on this. And then there's a graph. And you're going to plot some data, just like a scientist would. And that's what's going to basically help us divide our layers of the Earth. Now, let's see what time it is. We have 6:30 right now. We need at least another 30 minutes after this thing. So we need to make sure that we don't spend more than 30 minutes plotting these. As soon as you're done, let's stop and we'll talk about it so we can finish up the rest of the lecture.
So go ahead and read all this and do these two.
Right, just do that. All right, if you compare your graph that you just made to this graph of what scientists has done too, you notice that as you start at ground level, as you go up in the air, just as you would expect, the air temperature increases. But then suddenly, for a while, the air temperature stays the same. I mean, it's still cold, but it's staying the same. Then it has that inversion where it starts to increase. There's a layer in the atmosphere where it's actually going to get warmer the higher you go. Then notice on your graph that suddenly, okay, the temperature stays the same for a little while, and then it goes back to decreasing temperature quite rapidly and very, very cold. Then you see that area again where the temperature stays constant for just a little bit, and then it switches directions again and gets warmer. Very, very warm. Okay. So each of these divisions is how scientists divide our layers of the atmosphere, and they have names based upon if the temperature is increasing or decreasing. All right. So I've given you a chart on your handout that you're going to be filling in. We're going to be comparing the layers of the atmosphere. So I have up here the layers of the atmosphere in order from, my number 1 is the lowest layer, so you want to go to the bottom of your chart, and in this white, and right there, fill in the word troposphere. Let me pause my slide here. I'll pull up your paper so you know what you're doing.
Okay.
So in your bottom layer, the closest to the Earth, this is your ground of your Earth. Let's pretend that down here is your Earth. The first layer is the troposphere. Then you have that layer where it's very small area, but as you go up, the temperature stays the same, and that's called a tropopause. Just like pausing on pushing pause on the video camera, pushing pause on the video recorder, the temperature stays the same. So it's like, okay, you want to stay put where it's at. So you push pause. So you have the troposphere, then the tropopause. After that layer, let's look at my slide there. I'll pull it up for you. So you can maybe open up your notes side by side so that you can copy these down. Yeah, that might help you. So you have your troposphere, and then you have your stratosphere is the next layer, and then it's the stratopause. You see the pattern? The next layer is the mesosphere, and then the mesopause. The final layer of our Earth's atmosphere is the thermosphere. And if you notice, I have a dashed line on your packet because after that, you're going into outer space, which we call the exosphere. So that's outer space. So go ahead and fill in your layer names right now. So the last layer is not really a layer, it's the exosphere. That's outer space, so that's not considered the Earth's atmosphere because that's going out. All right, so let's learn about each one of these layers. Let's see, make sure. The 8 layers are defined by the constant trends in average air temperature, which changes with pressure and radiation. That means the rays coming from the sun that heats up there. Where the outer exosphere is not shown in this graph here that I have. So our first layer is called the troposphere. The temperature decreases with height in this thing. So on your chart, you have a column that it just asks you, are you increasing or decreasing? You can abbreviate those if you want. It's here. Okay. So we have a decreasing temperature with its height. And it varies around the globe, but the average is about 11 kilometers, so it's right in there. So for your altitude, you want to say, maybe you can put a little squiggly or write about 11 kilometers. The height of the troposphere will actually change from day to night and summer and winter. And we'll explain why here in a little bit. So one of the special properties is the layer's height will change. And maybe you want to write that in the special property actually of the tropopause. So that pause or that area where it's going to remain constant, it's going to go up and down.
So right in the tropopause
Yeah.
change.
So the warmer it is, for example, in the daytime or in the summertime, that tropopause is actually going to be lower than in the nighttime or in the winter time. I'm sorry, strike that, reverse it. It's generally higher in the summertime and lower in the winter time, but I think I was right about day and night. Yeah. Okay, so we need to, do you write that in your special properties?
Yeah.
Okay. So the tropopause separates the troposphere from the next layer, the stratosphere. It's generally higher in the summertime and lower in the wintertime. The other thing you need to know about the troposphere, it's besides the lowest most layer in the atmosphere, it has a decreasing temperature, I said that, yeah. Average rate of 3.5 degrees Fahrenheit per 1,000 feet. So when I say the temperature, you want to say 3.5 to about 6.5 Celsius. Okay. The troposphere is where all Earth's weather occurs. That's big and very, put that in the special properties of the troposphere. That's where weather occurs. Your wind, your rain, your hail only occurs on that very bottom layer of the Earth's atmosphere.
All the elements and stuff like that. What do you say that again?
All the weather.
All the weather.
Okay? So all weather is in the troposphere. Not tropopause, troposphere. That's huge. The boundary that divides the troposphere and the stratosphere is called the tropopause. It's located at altitude around 5 miles in the winter and around 8 miles in the summer, as high as 11 or 12 miles in the deep tropics. When we get into stratosphere and talk about the stratosphere, you'll understand why that changes a little bit. It's about 5 to 8 miles high. That's all the weather in the Earth's atmosphere. When you see a top of a thunderstorm that's flattened out or in an anvil cloud, it's called an anvil cloud. Do you see how in these pictures, these clouds, see how the top of the cloud just starts to, it looks like an anvil, if you know what an anvil is. An anvil, like in medieval, or anybody who does hammering or malleable metals and stuff, they have to hammer it on this thing. And it looks like an anvil. That's why it gets its name. You notice how it's all top on flat? Have you ever looked up in the sky and watched a cloud? Like, it looks like it's getting all nice, pillowy, and buffalo, and cotton ball. Then all of a sudden, the top of that big fat cotton cloud just looks flat. Okay, it's actually because it's reaching the top of the troposphere. It's hitting that troposphere. Something's preventing it from going even any higher. All weather, clouds, all that weather is always in the troposphere. Okay? What causes that to be flattened is it's bumping against the stratosphere. So there's something about that stratosphere that's keeping it down. Remember I said earlier how all those molecules and stuff are in the lower atmosphere? We got a lot of pressure in our lower atmosphere, and our pressure starts to decrease. So all those molecules has to stay down low in our troposphere. Okay, just a continuation. Our weather and climate. Weather is composed, and I think at the below your chart there's some fill-in blanks about weather. So the differences between weather and climate. Weather is comprised of these elements here. Air pressure, temperature, so those play a huge part in what occurs on Earth as our weather. Humidity, aka water vapor in the air. Clouds, aka water vapor in the air. Precipitation, aka water vapor in the air. Visibility. Okay, so sometimes they describe our weather based on how well you can see or not, aka smog, fog, yeah, and wind. So when they ask what the weather's outside, those are the things that they measure or will explain to describe weather. Now, not to be confused with climate, though, which climate is kind of like weather. It's weather over a long period of time. Okay, like they say, like 30 years. What's the general weather patterns over a 30-year period? Okay, and that's the average weather, so it's called a climate. All types of precipitation are considered weather. I don't know that I have, it's not important that you write. I think most of you know this already. Yeah, we know different precipitation. This is water vapor coming down from our atmosphere onto the ground. Well, how can it come down as? Well, it can come down as rain, it's wet, sleet, it's cold and slightly solid, hail, pretty solid, hard, snow, and freezing rain. So those are all the different types of precipitation coming down. And that's always in what layer of the atmosphere?
Always in the troposphere.
In the troposphere, yeah. The next layer up is called the stratosphere. In the stratosphere, at the top of that, there's this layer of ozone, or O3 oxygens. Three oxygen molecule, or the three oxygens joined together called ozone. So this is where you've heard possibly before the ozone layer. So in your stratosphere, special properties, write the word ozone. That's pretty important. The airflow in this layer is almost always horizontal. It's going side to side. So think of that anvil cloud. If that cloud is rising up and then all of a sudden hits that stratosphere, and the stratosphere, the air is traveling from side to side. Do you understand now why that anvil the cloud kind of hits the ceiling, and then it only has it's getting pushed either forward or backwards. So that's what's causing it to look like that anvil. See, the thin ozone layer in the upper stratosphere is a high concentration of ozone, particularly reactive form of oxygen. This layer is primarily responsible for absorbing ultraviolet light for the sun. It basically traps that sunlight in. The sun rays go to, let me draw this so you can understand what we're talking about here. if you got the Earth, and yeah, we've got that troposphere, but then you have your stratosphere, and inside that stratosphere, you've got this ozone. Oops. Back that up. Let's see. You've got this layer of ozone that's at the top of that stratosphere. What that does is as the sunlight comes in from the sun, it hits the Earth and it bounces back, but the ozone layer traps it and keeps it from just escaping out of the atmosphere. So all that heat that's coming from the sun then is trapped. And then that's why, that is why that next layer starts to get warmer. It's holding in all that heat. That makes sense? So that's why the temperature actually starts to rise as we get into the next layer, that stratosphere. The formation of this layer is delicate matter. It says, since only when oxygen is produced in the atmosphere is it called ozone, and formed to prevent the influx of ultraviolet radiation from reaching the surface. So not only is it doing that, it's also protecting us. So ozone up in the air is a good thing. It's protecting us from that ultraviolet radiation. So not only is it allowing some radiation in to keep us warm, it's actually also creating a barrier from the bad radiation that's coming from the sun and getting blocked, and that's going off back out into space again. So we need ozone. Okay, we just need it up in the air. We don't want it in the form of smog. Now, there's been some things that say that have been depleting our ozone layer. We're finding out that like chlorofluorocarbons used to be in like hairsprays and stuff like that. It was actually eating away at that ozone layer and making it thinner and thinner and making gaps where more of this ultraviolet radiation was actually getting in and getting down to us, which is a bad thing. We don't want that. Okay, if you're needing the altitudes and temperatures for those other columns, you can get that from the previous page, so you can just fill those in later. Just make sure you get the information. We know the stratosphere, though, as far as the layer goes, it's much larger than the troposphere. That troposphere, it was how many miles up? Look at that previous page. Or here we can kind of see now, actually. The temperature inversion of the stratosphere. So we know that that troposphere is roughly 11 kilometers up, but the stratosphere is from 11 kilometers then to almost 50 kilometers. Yeah. So we're talking 40 kilometers compared to about 10. It's about 4 times the height or width. So I've got a video to show you. This is a guy who's attempting the world record of free falling. So free falling means that we've jumped from the plane or wherever, and how long can we stay in the air? All right. So he's going to try to break this record. How long can I stay in the air for however high I've dropped? Let's see if it'll play from here. So world record. Let's see if he makes it. He's not in outer space. He's still in our atmosphere.
Okay.
He's actually in our stratosphere right now. So he is very, very... You can see the clouds down below. That's how we know that we're in our stratosphere, because look how far our clouds are down. I think they're going to show you... You see how long he's free falling for? They have that up there on the... Let's see if I can turn this up. You see that they have the miles per hour, how fast he's going? Kind of watch that. So is it getting faster or slower right now? It's getting faster and faster and faster.
Because the pressure's increasing, as it's going down.
Okay, we'll keep watching it. So he's going faster and faster. Look at him. Is he? He's kind of spinning all around there.
It's going faster than it did up here, you were talking about toward.
Now, when you think of somebody doing a high dive or jumping from a plane, is that the position that somebody normally jumps from a plane? What do they usually look like?
When they watch
That they usually do that? Is that the way his body is?
Mach
No.
1 erreicht mit dem Blick nach Mission Control.
So one thing you're going to notice here, and it's going to be unusual, and maybe you can help explain it, is he's actually going to start slowing down. What in the world is going to cause him to slow down? This is not the pressure.
Jetzt ist er stabil und ist unterwegs. Ich habe einen Riesenschreck bekommen. Hoffentlich ist
Why is he
alles
wearing a
gut
spacesuit?
gegangen. Jetzt in der stabilen Lage. Da hat sich der weiße
Okay.
Punkt doch wirklich gedreht. Unglaubliche
No oxygen.
Geschwindigkeit.
Where is that yet?
Wahnsinn, und der rennt dann noch zu uns. Und Riesenjubel natürlich.
It does look like he's in outer space because what atmosphere is clear, right? We can't really see it until we get to that clouds. That's the only way we'd be able to see it if it got cloudy. So he's in the air. He's still 3 minutes and he's still falling.
Stabilize Rock, wir haben schon Dinge gehört. Wie ein Fels. Jetzt geht es darum, den Fallschirm zu öffnen, aber da gibt es wie gesagt auch Notsysteme. Der Notfallschallschirm ist nicht aufgegangen und wir wären in einer hohen...
Yeah, kind of a little halo. Yep. We'll talk about that little halo too.
Keep talking, Felix, keep talking.
Red ruhig weiter, sagt er.
4 minutes. He's still falling.
Noch 6 Minuten Sauerstoff, also alles super. Wie gesagt, Fallschirm öffnen dann in 5000 Fuß.
He's trying to beat this record of 4 minutes and 34 seconds. There you just saw his parachute. Okay, so 4 minutes and 19 seconds and his parachute dropped and he was trying to beat the 4 minutes and 30. So he missed the record by, around 10 seconds here.
Felix, I hear you. Go ahead.
All right, I'm going to stop this and we're going to talk about this. Okay, so I have some questions for you. So why was he wearing a spacesuit? You said it already. I just want to get it on the recording. Yeah, there's no oxygen. Think if the air pressure is so low up there, so low, that means there's no oxygen molecules around him. As he's getting closer and closer to the earth, to the ground, there's more oxygen. So yeah, if he wasn't jumping for so high up, he would be jumping someplace where there's oxygen. But there's little to no oxygen from the height that he jumped. So he's in that spacesuit. Why would he be slowing down? I mean, he started to go pretty fast. He kept on going pretty fast until he got to 719 miles per hour. And then suddenly, he slowed down.
Well, he hit that, what is it called? He hit that constant.
The constant temperature. It's not really the temperature.
Okay.
The temperature wouldn't slow you down, but something else. Think about,
Pressure, that's good.
yeah, the pressure of the molecules that are in the air.
Yeah.
We said that 99% of all the gases that are in the Earth's atmosphere are in the first, how many miles was it, or how many kilometers it is? Really close, right? So that's back in your notes. You see, it would be like if you decided to go run down this hallway right now, you wouldn't have any problem running through it, right? So you could go run really fast. But if it was earlier in the day and it was a passing period and all the students were out there in the hallway, those students out in the hallway, that would be like more and more molecules. You'd have to slow down so that you could get around them. That's what he's doing. He's kind of getting around those molecules. It's holding him back a little bit. So that's why his body is slowing down. That's why there's more molecules, gases, closer to, in the lower layers of the Earth's atmosphere. So there's more gases in the stratosphere, or in the troposphere than there are in the stratosphere or in any other layer. in there. So we're getting fewer and fewer gases, so that's why we're slowing down. He doesn't meet the record for the free fall. Do we notice that? Oh gosh, but he did meet the record for the fastest. For the highest altitudes. So he was the world record for falling from the highest altitudes. But he still, even though he was up higher, think of it like this and like this, he jumped from here. The guy who has the record jumped from here. But this guy was able to stay in the air longer than him. What do you think that was? I made notice, or had you pay attention to the way he was falling. Do you remember? The way his body was, yeah, he was trying to go really fast, so he kind of had his arms together. He was trying to be like a rocket, but he was kind of, wobbling everywhere. Where a normal skydiver, what do? They put their arms and their legs out when they're falling to help get that more surface area for those molecules to help hold them back and stay up in the air longer. So the way you position your body is important. You got more things holding you up. And let's see. Okay, so that's what's the free fall. So our next layer of atmosphere is called the mesosphere, or think of it like the middle atmosphere. It's the one that's in the middle. If you got that exosphere on the other end. In the mesosphere, am I recording this? Oh, no. Yeah, I am. Okay. In the mesosphere, the air is very, very thin. There's hardly any gases or molecules up in this layer of the atmosphere. The pressure is very, very low because there's no molecules weighing you down, right? Notice that our temperature decreases in this layer again. It decreases rapidly. Why? Well, we don't have that ozone to help hold any heat in. All that heat is just escaping away now because the air is so thin, there's nothing to hold it in. If you are living in this region or in this region at all, you won't have any oxygen to breathe. So that's why the astronauts have to wear their suits and things. The air is super, super cold. Negative 90 degrees Celsius, negative 130 degrees Fahrenheit. Yeah, super, super cold. Especially near the top of the mesosphere. So very, very cold. Because there's basically nothing there.
Yeah. Exactly.
Suddenly, though, we go and we get to so we have the stratopause, that's where the constant, and then we went to the mesosphere, so the next would be the mesopause, where, yeah, it's cold, but at least it's not getting any colder. It stays the same for a little bit. Then all of a sudden, on our next layer, we are increasing dramatically our temperature. It is getting super hot. We went from super, super cold to super, super hot. The mesosphere, so above the mesosphere, is called the thermosphere. Think of like the word thermos. What's the purpose of a thermos? To keep you warm, right? Another name for this layer of the atmosphere that you'll sometimes see is called the ionosphere. It's the same thing, or it's in that same region. And the reason why it's called the ionosphere, too, is because it's where the layer in the atmosphere where atoms are ionized. Detached, okay? They're detached. They gain or lose electrons, so they have a negative charge to them. We're not going to go into real depth about that. You'll learn about that definitely in ICP. An ICP that you're taking. So the ionosphere is very, very thin. It's where the aurora takes place. Do you know what the aurora is? Okay, let me see if I can pull up a picture on the internet for you. You can sometimes, we don't see the aurora here in Indiana. If you were in Alaska, it is so beautiful. You'll heard about the aurora. Yeah, the lights in the sky. Okay, I really should still pull up a picture. I think we've got about 5 minutes here. Let me see if I can pause this. I'll pull up a picture for you.
Because it's so cold, it's losing its ion.
It's losing its electrons. So the electrons, when they lose their charge and they become negatives, they become what are called ions. Okay? It's very reactive, and it wants to bond with something, but if they lose their electrons and they're floating around. And so when they lose those electrons, it's like a little flash of light when it happens. So here we see that light, and they're often called the northern lights as a nickname, because if you go to the north or the northern part of the globe, you really do see these lights up in the sky, and it is just absolutely beautiful. And that is the uppermost atmosphere, layer of the atmosphere that occurs there because of those ions. It is beautiful. Okay, so the ionosphere or thermosphere is very thin. It's where the aurora takes place. It's also responsible for absorbing the most energetic photons from the sun. So we're absorbing lots and lots of sunlight. Think of it, the sun's rays are hitting that first, and that's why it's getting so hot. It also reflects radio waves. So this is the reason why radio waves can travel around the globe. Because you think rays can only usually travel in straight lines. By the way, are you getting some of these down in in the special properties?
Yeah.
Okay. So to give an example, if I could probably draw you a picture to help explain that. So if you have the uppermost part of the thermosphere and you've got a radio waves, let me pick a color so we can pretend that it's a radio wave. Let's pretend this purple line is going to be a radio wave. Let's say we're listening to a radio station, they transmit their signal. Well, the Earth is round, so if they sent their signal out, you would only necessarily be able to hear it from a short area. But because of this ionosphere, it actually blocks it and keeps on letting it travel around the globe. So a radio wave actually can be heard on the other side of the globe because of the thermosphere. So it reflects those radio waves, making long-distance radio communications possible. You heard of shortwave radios, that because it means, short distance. But there is the long waves that can travel all around the globe. And there's some very geeky people out there that had those types of radios, and they'll talk to each other from around the globe because they just think it's cool. I'm talking on a radio by waves clear across the globe. Personally, I can pick up my cell phone and talk to somebody. Okay. Thermosphere. Okay, so the thermosphere is the hot layer. Oxygen molecules absorb the energy from the solar rays of the warming air. So even though we have that oxygen, it is completely absorbed. Very few atoms or molecules are in this region at all. So the air pressure is very thin. Little to no air pressure at all. It's very, very hot. Think of if you ever seen like rockets, you've seen like the space shuttle coming in, re-entering from outer space. You see where it looks like it's burning up in the sky, basically. It's because it's entering that thermosphere. It's like, okay, we're out in space where it's very, 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 very cold, and then all of a sudden we hit that layer of the atmosphere that is super hot. And you'll notice on the bottom of the shuttles, you'll see those plates and stuff. I think Greg's going to show you pictures of the shuttle tomorrow and see the reason why those are there is to prevent the shuttle from burning up in re-entry. Yeah, it's because of that layer. Okay. Now, those were the main layers of the atmosphere. There are some additional, probably insignificant type of layers that they describe. They're kind of like the sublayers. Some people divide layers of the atmosphere this way, but very few. Okay, so we have the homosphere, and this is based on the air molecules. 78% is nitrogen, and 21% oxygen. So you can see the homosphere, where we can live. Notice that it stops at about this midway through the stratosphere. So about halfway up through the stratosphere, you cannot live without oxygen.
Right.
So everything else is called the heterosphere. And then the ionosphere, you see how it goes, the whole thermosphere. It actually kind of starts right around the mesosphere area, so that's why we call the thermosphere and the ionosphere. It's basically the same thing, but the ionosphere actually extends a little bit above the thermosphere and a little bit below, so it's a little bit wider than the actual thermosphere, but if you say what's the most important thing in the thermosphere, you would say that you've got your ions in their orbit. Okay. And the electric charge that's in that ionosphere, and that's what's there. So those are your notes for today. You have an exit ticket. Just kind of review and make sure you understand the main points of this lesson. Go ahead and complete your exit ticket and turn that in before you leave.